So I have heard it is being recorded now. Yeah, welcome also from my side. And you can see my name here, Wilfried Jacobs, here a picture with my wife in Rome. And I have also some hobbies traveling here, Perito Moreno Glacier in southern Patagonia, playing piano in the USA. I like astronomy, history, and also gambling. And some words about my professional work presently, advanced training, international cooperation, project management, also e-learning. And here I'm the expert head of the examination board, a diploma, dean of the University of Applied Science, and deputy chief of the training center. So that is very briefly to my person. And the structure, depending a little bit on the time, at not more than 10 minutes, I will show you a few things about Atlantic, the Atlantic Ocean, the ex-hurricane. Here's a, let's see the cursor. So, ex-hurricane Gaston, and then the trough above the Atlantic. Then in detail about over the UK and Ireland cold front as a wave, and I will show you some things about stress or tendency, wind direction, jet axis in this context. Eastern Europe, we have some warm precipitating clouds here. And then if you have some time, but I do not think so, a few convective cells about Eastern Mediterranean and fog stratus, but I think we will only cover the first three topics. So that is the surface analysis from the German Meteorological Service 0UTC of today. And here you see the ex-Gaston, the ex-hurricane, and then here's the frontal system. Here's no wave included, but we can see it a little bit here on the satellite image, but I will show to you later on here with our Ninjo system. Then we have here high pressure system over Middle Europe and some cloudy situations here and some showers more to the to Eastern Europe. So now I will close here the PowerPoint and I will switch over to our Ninjo system. I hope you can see it. So I will concentrate upon two, or here at 9 UTC here first upon the ex-hurricane Gaston, and here's the infrared enhanced, and you can see here some interesting low temperatures. You're up to minus 60 degrees roughly, and that here is the surface analysis of the 3-hour forecast with our icon model. And see here the core. And what is interesting in this case is if you consider the temperature, then you can see here also when I use here the cursor at higher temperatures, rough more than what's minus 7 degrees and around. It is a little bit warmer, typically for ex-hurricanes also when they enter in the middle latitudes. So that is one detail. Then I would like to come here to the frontal system of the low. I can also show to you, I think here the surface pressure, pressure, and I will switch off here again the temperature 500 hectopascal. Here are the centers of the low, and you can see here something like a wave included here, lower cloud top temperatures, sometimes heavy rain, and that is you see here not included in the 0UTC surface analysis by the Deutscher Wetterdienst, but you see here heavy rain. And when we consider in detail and consider here the surface pressure tendency, you can see here is in northwest peninsula difficult to see a rising or increasing surface pressure, and here falling decreasing surface pressure, and here high wind speed. So that is typically, you can see also here a very nice wave here in this cold front included. So when I now switch here to the day microphysics, there are also some interesting details here more over the Eastern European part. And yeah, this is a radar image, and you see here some low echoes are up to 30 dBz here somewhere. And when we consider that more in detail here with the help of the day microphysics here, then we can see, if I make it a little bit bigger, some interesting details here, for example, here near the southern part of the Baltic Sea. And if I switch on also here the infrared image, or it should work here, so at the moment. So now you can see it, yeah, minus 2 degrees, a little bit above 0 degrees, and this typical violet, so bigger drops and liquid water, and maybe that we have luck, and if we consider here the yeah, you see for example a shower, yeah, so here is a similar also not cold, sometimes yes, but not high extending clouds. So that is a detail here that is interesting, not a boring weather situation. Then you have here some foggy areas or low stratus, and this is interesting to see. If it is so more or less pinkish, then it is a bigger fog or stratus layer, whereas here we have it in a thinner form. Here is a similar situation, and you can see there is no idea coming from the surface observations. Yeah, so in other words, that day microphysics is a very powerful tool. So, and then I make it again a little bit bigger. I have 3 minutes left, and I will hand over to the students. So when we come here now to the Eastern Mediterranean part, and I will switch on now here the yeah, and also switch off here the surface. Yes, it is a little bit difficult to see. I try a little bit later here, 1 or 2 hours into the no, 10 or 11. Then we see here sometimes, yeah, here an yeah, convective cell high extending, and you see here with the temperature less than minus 50 degrees, and also small ice particles. Yeah, that is since the days here happening, yeah, thunderstorms here, yeah, near yeah, Turkey, eastern parts, Turkey and far to the east. So I will see what I have still open. I told you something about fog stratus and something about the convection. So I think that would be enough for me. We have now 10 after 2, and so I would like to hand over to the 2 students. They can introduce themselves, and they will have the opportunity to look a little bit to the some days, weeks, yeah, back. And so from my side, that's all. Are there some spontaneous questions now?
Yeah, maybe we'll leave them for the end.
Okay, fine.
Maybe.
Again, thank you, and I will stop sharing. Yeah.
Yes, thank you, Wilfried.
Yeah.
All right, then I start sharing my screen. All right, so you should now see my presentation. First of all, my name is Lennart Bock. I'm a trainee from the German Meteorological Services and for later use as a flight weather advisor. And me and my colleague Julia Silov-Tepić will talk about 2 weather events that have been happening this September. First, I'm going to talk about some severe thunderstorms in France and Germany on the 6th of September. And later, Julia will talk about Hurricane Danielle from the 3rd to the 4th of September. So first of all, I'm going to start with a surface analysis chart from the 6th of September, 12 UTC. I've chosen this event specifically as it marks the end of a very long dry period that for many regions across Europe has been the first time that they have experienced rain again. And it came along with various severe weather events, mainly thunderstorms and heavy rain showers. Over here, we can also already see ex-Hurricane Danielle, also with a warm front, but Julia will talk later about it, and it won't be significant for what I'm going to talk about now. What is more important is this low pressure system here, west of Ireland, called Peggy, with its occlusion here, which is influencing much of Western Europe at the moment of this analysis chart. We can also notice here a high pressure system over Eastern Europe and Southern Scandinavia. And wedged in between the two, we can also see a small warm front here, and which is what is going to be especially important now are these two lines of convections, one here over southern France and northern Iberia, and one over southern Germany, which are going to be responsible for the events I'm going to talk about now. So starting off with a natural color RGB from 15 UTC on the same day, we can already see, if we first look at France, that in northern France we have a lot of cyan over here, which indicates high, thick ice clouds. And if we go to the south of France, we can see that we got even brighter hotspots of cyan in these two cells down here, which indicate that we got even colder ice clouds and on top. And these two at the bottom, I'm going to deconstruct a little bit further by dissecting the natural color RGB of this specific cell here. As we can see in the near infrared, we got quite a low response, which indicates and correlates with cold clouds and ice clouds, as we would expect from the color. And then we also got our visible channels 0.8 and 0.6, which have a very high response with 100%. And as they correlate with optical thickness, we can deter that these are very optical thick clouds. And when we compare to the ground analysis chart, we can see that they also roughly coincide with the convergence line we saw earlier. Moving on to the day microphysics RGB, we can analyze these cells down here further by analyzing the cloud's microphysics. We can also, going back to the low pressure system we had of west of Ireland, when we look at the clouds and their shape and their structure, we can also see their rough movement and their winds. And now going back to the cell here, when we compare to natural color RGB, they roughly correlate with the clouds. So clouds we can see on the natural color RGB are also seen on the day microphysics RGB. And when with this point here, which I've also shown in the RGB colors preview, we have a very bright orange. And when we dissect the channels again, the red component responds with optical thickness again, which, as we've seen earlier, has a very high response. The green channel correlates with particle size, and we got a medium response there, which indicates that we got smaller particles than in a regular high cloud. And the blue channel correlates with temperature, where when we got a very small response, it means that we got a very low temperature. From all of this, we can deter that this is a very optically thick high cloud with small ice particles. And the small ice particles are a sign that we have lots of convection and strong convection going on there. And when we want to analyze this cell further, as we couldn't make out any hotspots, we can switch to the severe storm RGB. We got still the one cell selected, and as we can see, it's again red-orange with some small yellow spots, which are very important. When we dissect the channels again, we have a high response in the red channel, and the red channel indicates when we got a high component, we have high-level clouds present. The green component correlates with whether or not we have, again, particle size and also temperature. And as we have a high response there, this means we have very small particles again. And the blue component shows the phase of the cloud with low response, means we have an ice phase and a high response that we have a water phase. And from this, we can see that we have a high ice cloud with small particles once again. And because we got a very bright yellow there, we can now see what is the hotspot. And as I've said earlier, we got a cumulonimbus cloud here with very strong convection. And to the east, with the colors, you can see also we got very high ice plumes that extend quite a lot to the northeast, even to the border of Switzerland. All right, going back to the natural color RGB, I will now come to Germany. This is the same natural color RGB as I had before. Now, only that now we got 16 UTC. And now I have a question for the chat. I have this cell here marked out in the area, and I ask you to type in and would like you to write in chat, what do you expect in the orange circle according to the natural color RGB above, which you can see here. Gives you a minute or so. All right, so to answer the question, as we can see, we have once again a cyan color coming from the high response in the green and blue channels and a low one in the red, which shows us that we have optically thick high ice clouds once again. Now looking at some other interesting things, we also can see this band of clouds and ice clouds over here, which roughly correlates with the warm front we saw in the surface analysis chart. And unlike France, to differentiate between the two cells, in France you have this really big ice plume extending to the northeast, which isn't present here, so we got a much smaller ice plume. And what's also noticeable is that if we take a look at the Alps and southern Germany and Austria and Switzerland, we can also notice some bands of strong convection, which are typical for the region. And now also switching to the day microphysics RGB again, we can see if we compare the colors again, we have a very slight orange, more leaning towards the red, which the main difference comes from that we now got a lower response in the green channel, which indicates that we have a higher, bigger particle size. And so we can say that we got a little bit less convection here compared to France, but the convection very much is still noticeable. And also because we have lower convection, we also don't have that big of an ice plume. And if you also look to the east, we can see we have a lot of blue, which shows us one of the problems with using RGBs that use visible channels, as visible channels become unusable during the night, as everything will be black pretty much. And to end this, I have brought you some pictures from Offenbach on the day, from the headquarters of the DWD. The upper pictures showing from 15 UTC, the left one facing to the west and the right one to the east. And the same with the bottom, just at 16 UTC. And as we can see, if we look to the west, we can already see this very big ice plume from the cumulonimbus cloud that we saw earlier in the RGBs. And when we face east, we can also see that the ice plume is already creeping in from the left side of this picture. And just an hour later, we can see that it has drawn in very much closer. We can already see some precipitation down here. And the ice plume is now covering the city. And when facing east, we don't see the cloud itself, but we can see that the ice plume has extended and the general scene has dimmed quite a lot. So we can definitely say we got a broken sky or like even overcast, depending on which areas you want to highlight. And now Julia will take over and talk with you about her ex-Hurricane Danielle.
Thank you, Lennart, for that. I would like to start my part of the presentation with a question. When would you speak of a tropical cyclone? I would like to that you put your answer in the chat as well. We got 3 potential answers. Just put in A, B, or C. So I saw quite good answers there. I would like to start with a general overview. A tropical cyclone is defined by its wind strength. The wind speed needs to be above 118 km per hour. In order to reach this speed, the following parts must come together. The water temperature must be at least 26.5 degrees Celsius. In general, in an area between 5 and 20 degrees of latitude north or south of the equator, the solar radiation has to be vertical. And the last component that is needed is the Earth's rotation. Why is it so important to identify tropical cyclones? If such wind speeds meet land, extreme forces are generated due to friction, and the potential damage is depending on the wind speed. Additionally, cyclones push storm waves in their front towards the land. These waves, along with the heavy rainfalls a hurricane brings with it, are the reason for extreme flooding. Now I'm going to talk about Danielle. When looking at the surface analyzed charts beside the hurricane here in the west, we can see a low pressure area located in front of the British Islands, and the blue line indicates a cold front. Additionally, in the south of Greenland was another cyclogenesis. In connection with that, we got a warm front and a combination of cold and warm front, as well as a occlusional front here to the north. The isobars show the low pressure in the eye of the cyclone, which is typical. I will give you some more information about that later. Now going to the natural color RGB. The fronts we saw at the surface analyzed chart, we see as well in the natural color RGB as clouds. Here, the Danielle hurricane and the low pressure systems. This RGB has already been presented by Lennart. The cyan is an indicator for thick ice clouds with large ice crystals in higher levels here as well. With the help of polar orbiting satellites, it is possible to analyze the wind speeds in the cyclone. ESCAT is a product that shows speeds up to 45 knots in purple in the eye, and up to 20 knots here in yellow at the edge. The wind barbs make the cyclic rotation visible. ESCAT stands for Advanced Scatterometer. It is a microwave radar instrument on board the EUMeTsat Polar Orbit METOP satellites, and it estimates wind speed and direction over the ocean. Scatterometers are active radar instruments and therefore both emit and receive microwave radiation. This radiation has the advantage of not being affected by clouds, and this is why scatterometers are known to be able to scan the surface in almost all weather conditions. For additional information about ESCAT, I'd like to refer to the case study about Cynthia storm from EUMeTrain, or here also follow with the link and you will get to these informations. The water temperature in the developing area of Hurricane Danielle was between 26 and 28 degrees Celsius. Southern of that, the water was even warmer with 30 degrees Celsius. In comparison to that, the temperature underneath of the other two cyclones are significantly lower at this time with 18 degrees Celsius or even less. Unlike the natural color RGB, you can use the dust RGB both day and night. It is a combination of differences of various infrared channels. The dust RGB is perfect for monitoring clouds at day and night. Just have to look something. No. cannot start the video. Why is it?
Try exiting the presentation just and running it in the PowerPoint as we did yesterday.
It's not shown for me here to start. So yeah, okay. Now we are seeing the building of the eye in the dust RGB of the hurricane, and the dust RGB is perfect for monitoring clouds at day and night, as I said already. Red is indicating thick, high and cold ice clouds. Brownish shows thick mid-level clouds. In the animation, you can see the formation of the eye of the cyclone, as I said already. Here is this eye perfectly visible. I would just take the presentation so as it is now without the presentation mode. Hurricane Danielle had a pressure of about 990 hectopascal on the 3rd of September. Typically, the distance between the isobars gets smaller. The close, wait, my sharing stopped. I just heard no. So yeah, the isobars get smaller the closer you get to the center. As we can see here as well, we are decreasing with the pressure. And then, as you already heard from Mr. Bock, the severe storm RGB is ideal for monitoring convection and the microphysics of clouds. Yellow indicates a very cold top of thick ice clouds with small ice crystals and often the most severe convection. Red, on the other hand, indicates thick ice clouds with large ice crystals at the top. But always remember that the severe storm RGB is only useful at daytime, so that is why we only put together some pictures of the day, and I will just start it again. We can see here that we have really high convection, and that would be it from us. Thank you for your attention. If you have questions, do not hesitate to ask. Otherwise, we wish you a nice afternoon.